let's say we have some object that's moving in a circular path. So let's say this is the center of the object, the center of the path right over here, the center of the circle. So the object is moving in a circular path that looks something like that, a counterclockwise circular path. We could do that with clockwise as well. And what I want to do is think about how fast it is spinning or orbiting around this center, how that relates to its velocity. So let's say that this thing right over here is making 5 revolutions every second. 5 revs per second. So in 1 second it goes 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's doing that every second. It's making 5 revolutions. So how could we relate that to how many radians it is doing per second? Remember, radians is just one way to measure angles. We could do it how many degrees per second. If we did degrees, each revolution would be 360 degrees. If we do it with radians, we know that each revolution is 2 pi radians. 2 pi. If you go all the way around a circle, you have gone 2 pi. You have gone 2 pi radians, which is really just you're saying you've gone 2 pi radii, whatever the radius of the circle is. And that's where actually the definition of the radian comes from. So if you're going 5 revolutions per second, and they're 2 pi radians per revolution, then you could do a little dimensional analysis. These cancel out, and you see you get 5 times 2 pi, which gets us, so 5 times 2 pi gets us 10 pi radians per second. And it works out with the dimensional analysis, and hopefully it also makes sense to you intuitively. If you're doing 5 revolutions a second, each of those revolutions is 2 pi radians. So you're doing 10 pi radians per second. You're just going 1, 2, 3, 4, 5. So that gives us 10, or 2 pi radians. Every time, you're doing that 5 times in a second. So you're doing 10 pi radians per second. So this right here, either 5 revs per second or 10 pi radians per second, they're both essentially measuring the same thing. How fast are you orbiting around this central point? And this measure of how fast you are orbiting around a central point is called angular velocity. Angular velocity. And it's called angular velocity because if you think about it, this is telling us how fast is our angle changing. How fast, let me write it this way, speed of angle changing. And when you're dealing with it in 2 dimensions, and this is typically, at least in an early physics course, how we do deal with it, even though it's called angular velocity, it tends to be treated as angular speed. It actually is a vector quantity, and it's a little unintuitive. The vector is actually popping out of the page for this. It's actually a pseudo-vector, and we'll talk more about that in the future. So it is a vector quantity, and it is dependent, the direction of the vector is dependent on which way it's spinning. So for example, when it's spinning in a counterclockwise direction, there is a vector. The real angular velocity vector does pop out of the page once you start thinking about operating in 3 dimensions. And if it was going clockwise, if it was going that way right over here, the angular velocity vector would pop into the page. The way you think about that, right-hand rule, curl your fingers of your right hand in the direction that it is spinning, and then your thumb is essentially pointing in the direction. Your thumb is pointing in the direction that the actual vector, the pseudo-vector, is going to go in. But we don't have to think too much about that. For our purposes, when we're just thinking about a 2-dimensional plane right over here, we can really think of angular velocity as the official term is a pseudo-scalar, but we can treat it as a scalar quantity as long as we do specify which way it is rotating. So this right over here, this 10 pi radians per second, we could call this its angular velocity. And this tends to be denoted by an omega. A lowercase omega right there. An uppercase omega looks like this. Lowercase omega is what people tend to use for angular velocity. So there's a couple of ways that you could think about it. You could say angular velocity is equal to change in angle over a change in time. So for example, this is telling us 10 pi radians per second. 10 pi radians per second. Or if you wanted to do it in the calculus sense, if you want to say instantaneous angular velocity, and don't worry about this if it doesn't make a ton of sense to you, but this is just instantaneous angular velocity, it would be the derivative of your angle with respect to time, how the angle is changing with respect to time. Now with that out of the way, I want to see if we can see how this relates to speed. How does this relate to the actual speed of the object? So to get the speed of the object, we just have to think about how far is this object traveling in every revolution that it's doing. And what we can do right over here, let's say that this radius is r. So in every revolution, it is traveling 2 pi r, let's say this is r meters. Give ourselves some units right over there. So the circumference over here is going to be 2 pi r meters. And if the let's say that the angular velocity, let's say it is equal to omega radians per second, radians per second. And so how many revolutions is that per second? Well, we could go backwards from what we did over here. We have 1 revolution is equal to 2 pi radians. And sometimes, just to be clear, sometimes angular velocity is actually measured in revolutions per second, but the SI unit is in radians per second. And so if we want to convert omega radians per second into revolutions per second, radians cancel out. We are left with, we get omega over 2 pi revolutions per second. But we know how many meters we get per revolution. We have 2 pi r meters per revolution. So let's write that down right over here. So we have, let me copy and paste this. So our angular velocity, if we want it in revolutions per second, is going to be omega over 2 pi revolutions per second. Omega is in radians per second. If we put it into revolutions per second, omega divided by 2 pi revolutions per second. And then let's multiply that. And let's multiply that times, we want to convert this into meters per second. So how many meters do we have per revolution? Well, we're going to travel our whole circumference per revolution. So we're going to have 2 pi r meters per revolution. So these two cancel out. The 2 pi cancels out with the 2 pi. So you end up getting omega times r. Omega times, let me write the r in white, omega times r meters per second. And just like that, we have the magnitude of the velocity, or I guess we could say the speed of the object as it goes around in a circle. So what we can say is the magnitude of the velocity. I'll specify that by v. I want to be clear. This is not a vector quantity. It's not the velocity. It's the magnitude of the velocity. Or we could say this is the speed is going to be equal to omega times r. So the speed, v is equal to the angular velocity times r. I guess we could say the magnitude of the angular velocity times the radius. So let me write that out in words. And I don't want you to be confused. I'm not saying that this is a vector quantity. If this was a vector, I would put an arrow right over there. And if this was a vector, I would put an arrow over there, and then I'd be referring to the thing that's popping out of the page. But here I'm just talking about the magnitude of the angular velocity. And so writing it in words, you get speed is equal to angular velocity, and if you want to be particular of it, we'll say this is the magnitude of the angular velocity, times the radius of the circle that you are going around. And if you wanted to solve for angular velocity, you divide both sides by radius, and you get angular velocity, omega, is equal to speed, which we're using v for. So this is v, is going to be equal to speed divided by the radius. So we can actually use this information to do other interesting things later on, but hopefully this gives you a sense of how all of this stuff is related.